Now that we have gotten a brief overview of QuickCheck, we will apply it to testing of Plutus contracts. But there we encounter a problem, namely how do you use QuickCheck to test side affecting code that has effects in the real world, like on a blockchain. And that problem doesn't only arise with blockchains, it arises with all systems that use I/O, that have effects. And John Hughes himself always uses the example of, for example, a file system. How would you test file system operations, like open a file, write to a file, close a file, read a file, and so on, using QuickCheck? And the approach one can use there is very similar to the one that is used for Plutus. And the idea is that you start with a model. A model is basically an idealized model of how the real world system should work. So there must be some sort of relation between the model and the real system. So if the real system is a file system, then you could in the model have an idealized version of how you think files should work. And then what QuickCheck does in its random generation, it generates a random sequence of actions that you can perform on your system. So in the example of a file system, it would randomly generate a sequence of opening files, closing files, writing to files, reading files, and so on. And now you can basically step this model and the system in parallel. So you have some sort of action that you perform in the real world, and you apply the same type of action to your model. And then after that, your real system has progressed into a new state, and your model has also been updated. And then after this step, you can compare the two and check whether they are still in sync. And you continue this for several steps. So when our first QuickCheck example, we generated random list of ints, the idea for testing a real-world system is to generate random lists of actions and then apply those actions both to a model and to the real system and compare that the results are as expected and that the model and the real system stay in sync. And shrinking in this case would be if you have a list of actions that shows that there's a bug in your system, then you can, for example, drop some of the actions and see whether the problem still arises and try making this action list shorter until you can't drop any more actions from the list and still reproduce the bug. And this is exactly how the QuickCheck support for Plutus also works. So in order to test the Plutus contract, we have to come up with a model and define our expectations, how the various endpoints, for example, would change the model, and provide a link between the model and the real system, or actually it's not the real blockchain, it's the emulator, but it in a sense that is like a real system, and then apply this QuickCheck machinery. So that's what we will look at next for the example of our token sale contract. Before we look at the testing code, let's go back to the token sale module. And I needed to change something there for the tests to work. So earlier I just had this use endpoints, takes the token sale as parameter, and then provides these 4 endpoints: set price, add token, buy tokens, and withdraw. And now I also added the use endpoints prime, which has the same implementation, exactly the same implementation that the use endpoints had before, but I just changed the signature. So instead of just making it work for our fixed schema, this TSU schema, I make it work for every schema that contains these 4 endpoints. And we will see why I have to do that in a second. And then I just define use endpoints in terms of use endpoints prime. It's just the same implementation. It simply narrows down the schema to this specific one. So the code for this is in module spec.model, And here we see we import Plutus contract test that we saw before that provides basic support for testing Plutus. And now to use this quick check approach, we also import Plutus contract test contract model, which has all the machinery to define a model and link it to the real contract. Furthermore, we have test.tasty and test.tasty quick check. Test.tasty.quickcheck provides a link between quick check and tasty so that you can use quick check properties in tasty test suites. Before we come to the model, let's first look at those 3 lines here. So I define a slightly modified TSU schema that I call TSU schema prime. And it's the old TSU schema, but it adds an additional endpoint in it that takes an argument of type token sale. And the idea is that somehow we must communicate, once we have started the token sale, this token sale value to our use contract. Because remember, that is parameterized by value of type token sale. And this is somewhat tricky due to the fact how this property-based testing in the case of Plutus works. So the trick I'm using here is I use this extended schema, and then what I will do is when I start a token sale, I will call this init endpoint with the token sale I just started. And what does this init endpoint do? You can see that here. So it simply calls the use endpoints prime that we just looked at in the other module with the value that's provided in the endpoint. So I can start this modified use endpoints prime or double prime actually, because prime I already used there from the beginning, but the only endpoint it will expose in the beginning will be this init endpoint. So it can't do anything else. It can't interact with the token sale because there is no token sale yet. So at the moment I start a token sale, I will call this only endpoint, the init endpoint, and that will then kick off the one we have seen before that is then parameterized with the token sale. So it's a little bit tricky, but at the moment there is no better way to make that work. But this quick check library for Plutus is also still under very active development. So it's quite likely that things like that will become easier in the future. So to define the model, first define a data type TS state for token sale state. So that's supposed to represent the state of one token sale instance. And it has 3 fields: the current price, the current supply of Loveless in the UTXO in the contract, and the current supply of tokens in the contract. And now I define my model. That is now the model I was talking about in the diagram earlier. And that is just a map from wallet to token sale state. So the idea in this test is that I have several wallets, actually only 2, and all the wallets run their own token sale. So we will have 2 wallets, and each of the wallets will run a token sale contract, and we will have 2 tokens, and the 2 wallets will trade different tokens. And the idea to use a map is that in the beginning, before the contract has started, there won't be an entry for that wallet, and once the contract has started, there will be an entry for that wallet with the current state. And I also implement lenses for that, because we also need optics in order to interact with the library, with this Plutus contract test contract model library. And now all the logic is in the instance of the type class contract model for this type. So here we provide how our model should behave and how it is linked to the actual contract. So first we have a so-called associated data type. So that's quite an advanced Haskell feature. So in type classes, you can have, instead of just methods that we usually have, also have data types. We have actually seen that before when we define validators and we define this dummy type that provides a link between the datum type and the redeemer type. So there we also use these associated types. So we need an associated action type, which represents the actions that QuickCheck will generate. And in principle, I just have one constructor in this action type for each of the endpoints we saw earlier. I just have additional arguments because now there are different wallets at play, and I must keep track which of the wallets performs an action. So start wallet means that this wallet starts a token sale contract. Then set price wallet integer means that this wallet, the second one, sets the price for the token sale operated by the first one, and it sets the price to this integer. Of course, we know from the contract logic that this should only work if these two wallets are the same, because only the owner of the token sale can actually set the price. But to make it more interesting, I want to provide actions also if somebody else tries to, and then we can see whether this is actually not working, because we expect that nobody else can set the price of token sale owned by a different wallet. Same for add tokens. So again, add tokens. This wallet wants to add tokens to that wallet's token sale and this many tokens. Then withdraw. This wallet wants to withdraw so many tokens and so many ADA from the token sale run by this wallet. That should again fail if the two wallets are not the same. And finally, buy tokens. So this wallet wants to buy from that wallet's token sale this amount of tokens. Okay, so this is the first ingredient, that we need this type of actions. The second ingredient is another associated data type. It's called contract instance key. So the idea is for each instance of a contract that we are running, we want a key that identifies this instance. And this is actually a so-called general algebraic data type. So it's a little bit different format to usual data declarations in Haskell that look like this. So the idea is that instead of just providing the constructors, you write them in this form, basically with their type signature. So this means we have a constructor start key that takes a wallet as an argument and then produces something of this type. And the reason we need these GADTs here, or the point of GADTs, generalized algebraic data types, is that with normal data types, the type parameters are always the same for all constructors. So if we have a parameterized type like list, for example, list of A's, then all the constructors that we have will produce a list of the same type A. And generalized algebraic data types allow us to have different type parameters. And we need this in this case because our contracts potentially can have different type parameters. So in this case, there are two types of instances. Recall we had the start contract and the use contract, and they had different type signatures. And so I provide one sort of key that I call start key for the first type, for the start contract, and it just basically as an argument has the wallet that does the starting. And here we see, so the type parameters are, the first one is the model we are just defining, and then the ones that come from the contract itself. So the state type, which is last token sale, if you recall in this case, then the schema, and text is the error type. There's one additional type, this P here, which stands for parameter, and that would allow us to parameterize our contracts. So if they take a parameter, then we could use this P. But as you see in both cases, I use unit. And you might ask why, because this use contract, the second one to interact with the token sale, is indeed parameterized by something of type token sale. But the problem is that the token sale contains this thread token as one field, and the thread token has nothing to do with the model. I mean, the model talks about tokens and amounts of Lovelace and tokens and prices and so on, but it has no concept of a thread token. The thread token is very intimately connected to the actual runtime, to the execution on the blockchain. because we get this thread token, or the state machine mechanism gets it by looking into the wallet, picking UTXO, and then using this UTXO to mint the NFT and so on. So therefore, unfortunately, we can't use this P here to parameterize our use contract with the token sale. And that's the reason why I had to do these things here with the extended, with the extended schema and so on, exactly for this reason, because I can't use this P because the parameter that I need, the token sale parameter, doesn't follow from the model. I don't have enough information in the model to define this token sale value. And therefore I have to do this trick with this additional init endpoint. And therefore I can't make use of this P and just use unit here. So I pretend that my contracts are not parameterized. And indeed they are not. I mean, the start contract is anyway not parameterized. And with this addition of the init endpoint, I also remove the parameterization of token sale from the use contract. So this now doesn't have a parameter anymore. This use endpoint's double prime. And the trick is that by calling this init endpoint, I then can enable the other endpoints, the ones that actually do the work, with the value I pass into this init endpoint. So as I said before, it's a bit tricky, but hopefully will become easier in future. And then there's the second type of contracts, the use type. And so I provide an instance key for that as well, that I call use key. And that takes two wallets as parameters. This is the one that owns the token sale we are interacting with, and that is the one that actually runs the contract. So similar to how it worked here. So same order of wallets. And this has different type parameters. Again, TS model, but there is no state. We don't use tell, and the schema is different. The error type is the same. The next function, instance wallet, that we must provide tells the system how to extract the wallet that a given contract is running on by its constraint instance key. And this is simple. So for start key, as I said, the first parameter is exactly that, the wallet that does start the token sale. So start key W, the wallet that runs it is W. And for use key, where we have these two wallets, but as I said, my convention is the first one, whenever we have these two wallets, I always use the same convention. The first one is the one running the token sale, and the second one is the one interacting with it. So the first one is the one running the token sale, second one is the one interacting with it, and that's the one that's running the contract. So in the second case, in the use case, the second wallet is the wallet running the contract. The next method we need to implement is called instance tag, and that takes one of these keys and must turn it into a contract instance tag. And the contract instance tags are then used on the blockchain side, on the actual implementation side, to identify running instances of contracts and interact with them by calling endpoints. So the requirement for this function is that it must be injective. So different keys also result in different constant instance tags. So this contract instance tag type doesn't have an expose constructor. So I was a bit puzzled at first how I'm supposed to actually provide a value, but it does implement the type class isString. And that type class is the one we always use when we switch on this GHC extension, overloaded strings, that allows us to use string literals for other types, not just strings. So we have done that for a variety of types, including byte strings and text, I believe. So the way that works is that under the hood, when you have this overloaded strings extension activated and you use a string literal, then the type that you want to convert that string literal to must be an instance of the isString class. And the isString class has one method called fromString that takes a string and results in a value of the type in question. So whenever you have an
type that is an instance of is string, you can use from string and then a string to get a value of that type. And that's the trick I'm using here. So I implemented show, or actually I haven't shown you that. That's probably further down right here. So I'm deriving instance show for this contract instance key. I can't do that in the usual way, just putting deriving show after the definition of the type, because it's this generalized algebraic data type. So for those, the normal deriving doesn't always work. But there's something called standalone deriving, which is yet another extension that I activated here. And using that, you have this other syntax to derive instances. So it's deriving instance and then the class you want and then the type for which you want it. And that is more powerful than the normal deriving. So in particular, it also works for GADTs. So my construct instance key is showable. I can use show to convert a value into a string. And then I use this to define this instance tag function. So I just convert my key into a string. I prepend this string instance tag for. I wouldn't need to, it's just for optics. And then I use from string to actually convert it into this construct instance tag type.
So it is just important that this instant tag function results in a different tag for each instance that we will ever run in our simulation or in our tests. And this is guaranteed here because the way these are set up. So we will have one start instance for each wallet and then one use instance for each pair of wallets. But of course, they are all different values of this contract instance key TS model type. And then when we show them, they will still all be different. And that's the important part here. Actually, there's a default implementation for the instance tag method of the contract model class. So you normally don't have to implement that yourself, but that default only works, at least right now, if you only have at most one contract instance per wallet. But this is not the case in our case because we will have actually three per wallet. One start instance and two use instances using the own token sale and the other wallet's token sale. So we have three contracts running per wallet, and therefore we are forced to implement that ourselves, this instance tag function. So the next one, arbitrary action, as the name suggests, is supposed to generate an arbitrary action. So action we defined here, and we must now tell the system how to generate a random action. And as argument, it gets the model state. We come to that later, but I don't need that here and I can ignore it. One off is one of the combinators provided by QuickCheck, and given a list of arbitrary actions, it randomly picks one of those. So the idea is I basically just provide a list to create random actions of these types using these constructors and then pick randomly one of those. And this is using something that we also haven't seen before. It's so-called applicative style. So recall when we introduced monads, I mentioned that monad as a superclass has applicative, but we haven't used applicative yet. And applicative is often very useful to write monadic code more compact. So basically, what this says is first run the monadic gen wallet action, which I should show first. This is here. So what this is supposed to do, it's in this QuickCheck gen monad, this random generation monad, generate a random wallet. And how do I do that? I use yet another combinator provided by QuickCheck elements that simply takes a list of values of the type I want to generate and then picks a random of those elements. So wallets is another helper I defined somewhere here. So wallets is just wallet 1, wallet 2. So it's just this 2-element list. So gen wallet will just randomly either pick wallet 1 or wallet 2. Okay, so what this means is we first use this gen wallet to generate a random wallet and then return the action start that wallet that we just picked. And this is just a more compact way to write it. This, of course, this operator we have seen before, this fmap, which comes from the functor class. So gen wallet is of type gen, capital Gen wallet, and start, as we see here, start takes a wallet and returns an action. So if we fmap that, we get something of type gen wallet to gen action. So the result is something of type gen action as we want. So it's a random action. And here for set price, we must pick 3 random arguments. So set price takes 2 wallets and an integer. So we use gen wallet twice to pick 2 random wallets for these 2 wallet arguments. And then gen non-neg, which is also defined here as a helper function, which randomly generates an integer, but a non-negative one. And actually there is something in the quick check libraries to support this. There's a non-negative type that implements an arbitrary instance. And it's just a new type wrapper around integer, and with get non-negative I can extract the integer. So this arbitrary comes from the non-negative type that would generate something of type non-negative, but that just wraps an integer and I extract that integer with this get non-negative. Anyway, so this generates a non-negative random integer. Okay, and this is now where this applicative style really shines. So if I wrote that in a do block, for example, I would first call gen wallet and bind the result against something, whatever, w1. Then I would call gen wallet again and bind the result against something like w2. Then I would call gen non-neg, bind the result against p. And then finally I would return set price w1, w2, p. And using this operator, which comes from the applicative class, we can write this nicely and compactly like this. So conceptually, applicative is weaker than monad, and you can always use this applicative style if what you are doing, the actions in the monad you are invoking, don't depend on the result of previous actions. So in a do block, I can have some monadic action and then inspect the result, and depending on what the result is, do the one thing or the other. And that is not possible in applicative. But often monadic code doesn't make use of that power, and then we have this more compact way of writing it. But it's really just identical to using a do block. It's just more compact. Anyway, and I follow this same schema for the other constructors. So again, this one-off will randomly pick one of these lines, and then so decide on one constructor for an action to pick. So it will randomly pick a start action, a set price action, an add tokens action, buy tokens action, or withdraw action. And then once it has picked one, it will generate the random arguments for that constructor. Depending on what constructor it is, might be different types or number of arguments. So withdraw takes 2 random wallets and then 2 integers, non-negative integers, for how many tokens I want to withdraw and how many loveless I want to withdraw. I can try this out in the REPL. So using sample that we saw before, and then I sample this arbitrary action that I just defined. I don't have this model state, but I know I'm not looking at it, so I can just use undefined. And let's see. And I get a couple of randomly generated actions. And we see that it indeed picks different constructors, and then for those constructors picks random arguments. For example, here's withdraw, wallet 1, 3, 5. And here we have another withdraw, wallet 1, wallet 2, 1, 2, and so on. Next is initial state. As the name suggests, it's the initial state of our model. Recall the model was this map from wallets to tokens held states, and in the beginning there won't be any tokens held yet, So it's just the empty map. So the initial state is the model that has the empty map, which means no token sale has started yet.
Next method we need to implement is called initial instances. And as the name suggests, it gives the initial contract instances that have to run. And that's a list of something of type start contract TS model. And what's this start contract? That's a type that has a constructor with two arguments. And the first argument is a key, one of these contract instance keys we defined above. The second argument is a parameter. I mentioned this P parameter in the construct instance key type earlier that allows us to start parameterized contracts. But I also said that in our case, I'm using unit. So I just use unit here. I have to because unit is the only value of type unit. Okay, and those are the contracts that are supposed to run in the beginning when we start the test before we run any actions. And in our case, I want to start all of them. So a token sale for each wallet and then a use contract for each pair of wallets. So that's exactly what I'm doing here. So I'm using list comprehension syntax. So V runs over all wallets, and I have the start key V, and then V and W will be all pairs of wallets, and I take use key VW. So seeing as we have two wallets, each wallet will run three contracts, one start contract, two use contracts. So this should be a list with 6 elements, 2 start contracts and 4 use contracts. Now the next one, precondition, that allows me to say that some actions may not be legal in a given model state. And that's not always necessary. One can also put that into this arbitrary action thing here. So here I just indiscriminately pick a random of these constructors, but I don't make sure that somehow this is legal what I do there. So for example, none of these 4 would make any sense if the token sale in question hasn't even started yet. So we can use this precondition for that. So that, for example, we can say we can only start a token sale if it hasn't already started, and we can only use a token sale if the token sale has started. And that's what I'm doing here. So the first use is to not allow the generation of illegal actions. And that, as I said, could have been done here if I had done this in a more complicated way and actually inspected the model parameter that I get here. I could have excluded using these if the token sale in question hasn't even started yet. So that's one thing. But the other thing is also shrinking. So I said earlier that shrinking is a very important part of QuickCheck because often the random counterexamples, if there are counterexamples that you get, are very large. And if you look at them, you don't really see easily where the problem is because there's so much noise. And then the shrinking mechanism tries to reduce the counterexample that QuickCheck has found to the simple most possible example. And that's often very helpful because you know there isn't a smaller counterexample. This is the smallest one, and that often tells you a lot. As I also mentioned, in the case of IO testing, or here in our case, Plutus testing, where we have these random action sequences, shrinking in principle means that we try to drop elements of this random action sequence. So maybe we found a random action sequence that triggers an error with, I don't know, 20 steps. And then QuickCheck will try to remove some of these steps. And then after removing one, we'll check whether the shorter sequence that results from removing one still is a counterexample. And then it will iterate that. So it will try to remove steps, as many as possible, while still having a counterexample. But of course, if you remove a step, the actions could become illegal. So for example, I mean, set price only makes sense if the token sale in question has already started. So if we have a sequence where there's a start and then later a set price for a given token sale, that's fine. But now if during shrinking we happen to drop the start, that wouldn't make sense anymore because then the set price no longer is allowed. So we shouldn't drop the start in that example. And this is the second use that this precondition method is used for. So during shrinking, this is checked that all the preconditions are still satisfied. Otherwise, it won't drop the element in question. Okay, and so what I want to do here is I want to say the precondition on start is it hasn't started yet, and the precondition on the others is it has already started. And for all of those, I use this helper function here, get TS state prime S and W or V here. So that is always the wallet with the token sale. The V in the first, the W in the first case, and the V in these cases. So what's this get TS state prime S? So for that, we actually have to understand what model state is. And if we look in the documentation, first thing you see is that we don't see a constructor, so that is not exposed, not exported. So the question is, how can we actually work with that? But the point is, we have a couple of functions that operate on this model state thing. The most important one, arguably, is the first one, this contract state, and that is a lens from model state to state. So our state, in our example, this TS model in particular, is accessible from a model state via this lens. That's one of the main reasons why I had to introduce optics first, so that I can explain how to make use of this lens. So given a model state, whatever it is, we don't see the constructor. We know that we can focus on the state part included in this model state. So once we have a model state, TS model, we can get to an actual TS model. And then we see here there are other things that we can do with the model state. For example, there's also a current slot lens. Okay, it's not a lens, but it's an optic, it's a getter. So that means we can only look at it. We can see the value, but we can't set it. With lenses, getting and setting is possible. Okay, but so the model state not only contains this contract state, it also, for example, contains the current slot. And there are other things. It also contains the balance changes. So we can see for wallet how the balance of that wallet has changed and things like that. But I think in our example, we will only use these two, contract state and current slot. So going back to the code, now I think we can understand this helper function, get TS state prime. Let's see. Right, so given a model state and the wallet, I try to extract the token sale that this wallet is running. And the way I do it is, so given this model state, I now use this operator from the lens library that we saw before to view a lens. And what lens do I use? So first contract state. So now I have something of type TS model. And that was this new type wrapper around a map. So composing this with the TS model lens, I now have this map. And then there is a standard lens for maps defined in control lens in the lens library that for a given key allows me to zoom into the value at that key. But that is, I mean, it could be there or not. I mean, not every key does have a value. So therefore, this is actually a lens not to the type of values, but to the type of maybe values. So if I zoom into a key that isn't in the map, then I will get nothing. I will see nothing. And if I zoom into a key where there is a value, I will get just that value. And it's actually a lens, so I can also set it. And that can be used to actually delete keys from a map or to insert new elements. So if I set add key at a given key to nothing, I remove that key from the map. And if I set add a given key to just something, then I will insert that element into the map. But I'm not using that here. Here I'm using it for looking. So using optics, given the model state, I zoom into the model, then into the map contained in this model, and then into the value at the given wallet contained in that model. And that can be of type maybe. So in our example, that means if it's nothing, the token sale for that wallet hasn't yet started. And if it's just something of type TS state, then the token sale has started and this is its state. Recall this TS state was this triple consisting of price, amount of loveless, and of amount of tokens. So now we can understand this precondition function. So I always use this get TS state prime for the given state and the wallet I'm interested in. And this is now a maybe value, just if the token sale has started, nothing if it hasn't started. So the precondition to start a token sale is that it hasn't started yet. So I check whether it is nothing. This is nothing and this just comes from data maybe from the standard prelude. And for the other four cases, I want it to have started already, so I check that I get a just value. The next function is the most complex one and maybe the most important one. If you recall the diagram I showed you, then I said that for each action, we must know what effect that action will have on our model. And that's exactly what this next stage function is for. So it gets an action and then results in something in yet another monad, this spec monad. And the purpose of the spec monad is to describe effects on the model. And when I say model, that's first of all our TS model. So this value of type TS model, how that changes. But it's also additionally something about time passing and about value flows between wallets. So in this model, there is a concept of how much every wallet owns. And you can say in the spec monad that a given wallet earns some funds or sends some funds elsewhere. And you can say that time passes. So let's look at an example. So the start action. So wallet W wants to start a token sale. So the first line here says one of the effects of this will be that 3 slots will pass. This is a bit tricky to get the time right, so the model and the actual emulator must keep in sync as far as slots are concerned. So I probably use a bit more time than is strictly necessary, but I just wanted to make sure that basically it stays in sync. So I just use 3 slots. So I'm saying the starting of the token sale takes 3 slots. Now the next line is maybe the most interesting one. So this operator comes from the spec monad. And on the left-hand side, it takes a lens from the model. So not the model TS model, but the TS model. So from this, so from the value of our model to somewhere. And on the right-hand side, it takes the value of that somewhere. And then it will update the corresponding focus of the lens to that new value. So in this example, recall our TS model is a new type around a map. And with the TS model lens, we get to that map as before in this helper function I showed you. And then I'm using the add that I just explained at the key of this wallet. And that should be nothing now, what I get here, what that focuses on now, because the token sale hasn't started yet. So there is no entry for W in this map. And now on the right hand side, I give the new value. So I say insert a value now. And what should the value be? Well, there was this TS state, this triple with price, loveless, and token amounts. And in the beginning, the price will be 0 and there's neither loveless nor tokens in there. So this line says when I do the start token sale action for wallet W, then in the model for key W, there now will be a TSS state, and the values of this TS state will be 000. And the last thing is the effect on the funds of the wallet. So with withdraw, I say that the wallet in question, the argument here, loses funds. And why do I lose funds? Because when I start the state machine, when I start the token sale, I create a UTXO at the address of this token sale. And there's this min ADA rule that every UTXO must contain a minimal amount of ADA. So by starting the token sale, I have to pay that. So that's what I'm saying here. So to say it again, the effect of doing the start action will be 3 slots will pass. My model will change because now there will be an entry at this key W, and the entry will be TS state 000. And my wallet will lose min ADA, which is in the emulator, it's always 2 ADA. So the next action is set price. So set price by W for the token sale run by V to value P. And here I'm saying the effect will be 3 slots will pass. And if V and W are the same, recall set price is only allowed for the owner of the token sale, then the value of the model will update. And this is just another optic, IX. It's similar to add, but it's not of the maybe type. It's just of the type of values, but it's actually not a lens like add. It's a traversable. So it can or cannot be there. But we know in this case it must be there because we checked that in the precondition. So set price will only ever be called if actually the token sale for V is running. So this here zooms into the map, then this zooms into the value, so the TS state for the token sale. This lens zooms into the price, so that's I think the first component of this triple, and using this operator again sets it to P. So this says set price has the effect that 3 slots will pass, and if V equals W, then the model will change accordingly. So the price component here will change to P. Now add tokens. So for the token sale run by V, called by wallet W and with the amount N, 3 slots will pass. Then I ask whether the token sale has started. That is actually probably that's redundant because add token, because of the precondition, is only allowed if that has actually started. So probably that's like a remnant of an early iteration of the code where some of the preconditions were different. But anyway, how is this has started implemented? We saw this helper function get TS state prime. So from that I derived another helper function get TS state, which now works in the spec monad, but using this. So in the spec monad there's a function called get model state, which allows me to get the model state as the name suggests. So I just get the model state and then use this get TS state prime that I defined earlier to, given the model state, return this maybe TS state. And once I have that, I can define this has started also in the spec monad, but with return type bool. So I just use this get TS state V that I just defined here. So this is now of type maybe. And as we said before, if this maybe is a just, then the token sale has started. If it's nothing, it has not. So by F mapping is just over that, I can say whether it has started or not. So going back, so we will only do something if the amount of tokens to add is positive and if the token sale has started. To understand this line, let's look at ask model state. So given a function from the model state to some type A, we get an A in this monad M, and spec is such a monad, so we will apply this to the spec monad. So we must provide such a function going from the model state to A. A in our case is this value of a wallet. So balance change, I showed you that briefly earlier, is a lens or a getter from the model state to the wallet change, the balance change of wallet W. So using view, which is just another way for writing this caret dot operator from the lens library. So this is now a function from model state to value change. And now using this ask model state, I actually get that value in the spec monad. Now, that is not a Plutus value, it's something more complicated, something of course type symbolic value, because there is a mechanism that I'm not using in this example with so-called symbolic values. And I don't really want to go into that. But a symbolic value is basically a normal value plus some symbolic stuff. And I can extract the normal value with this actual val part function. So what this line does is the BC is now the actual balance change of my wallet W. And I want to check, I mean, the purpose why I'm doing this is I want to check that I actually have enough tokens to give. So tokens, I haven't showed you yet. That's a map from wallet to asset class. So for every wallet, it gives the asset class that that wallet is actually selling. So if you go back again, so this is the token that is sold in this token sale that we are now looking at. Okay, and now I check whether token amount, that's yet another thing I define down here. That's just 1000. So that's the original supply of tokens every wallet gets. So I check whether this original supply, when I then add the change, so the sum should now be how many of those tokens my wallet has right now, and that must be greater or equal to the amount of tokens I want to put into the sale. So I check whether the wallet has enough tokens to actually do this. And if it does, then the effect of this action will be that the wallet loses these tokens, because now they will be in the UTXO of the state machine of the token sale. And the TS model updates. So TS model at key V, the wallet we are looking at, the TSS token part, so the amount of tokens in that token cell will be changed. It will increase by n. So this dollar tilde is similar to the dollar equal. So the dollar equal sets a value, and the dollar tilde applies a function to the value. So this says the effect will be that the number of tokens in the token cell will increase by n. Okay, buy tokens. So token cell run by V, called by wallet W, amount of n. 3 slots will pass, and if the amount I want to buy is positive, I get the token sale state. I showed you that before. And I'm just considering the case that the token sale is actually running. If not, then nothing happens. But again, that shouldn't happen because buy tokens should, due to the precondition, only ever be called if the token sale is actually running. So I'm in this case, and T is now my TS model. So I check whether there are actually at least n tokens there, because I want to buy n. So this will fail if they are less than n. Then I look up the price given my models here. I calculate how much that will cost me. So L is now the price in Loveless to buy these tokens. Now the effect will be that I lose this amount of Loveless because that's the price I have to pay. This deposit is the opposite of withdraw. So withdraw makes this wallet lose funds. Deposit will make it gain funds. So I pay this amount of Loveless, but I get the tokens I am buying. And then the model also has to update. So the number of Loveless in the token cell increases by L. The number of tokens in the token cell decreases by N. Finally, withdraw. So token cell run by V. Wallet W wants to withdraw. N tokens, L Loveless. 3 slots will pass. Nothing happens if V is not W because only the owner of the token cell can withdraw. So again, I look up my state. Again, only this case can actually happen due to the precondition. So T is now my TS state. And I check that actually what I want to withdraw is there. So there are at least N tokens, there are at least L Loveless. And if that's the case, then my wallet gains L tokens and gains gains L Loveless and gains N tokens. And the model will be updated. So now there are L Loveless less in it and N tokens less. And that's it. So that's this next state function, which is, I think, the most complex one. Next, start instances. So we started our contract instances right in the beginning, but there's also the possibility to start them later. So given a model state and action, you can give a list of contracts that are supposed to be started. But in our case, that's simply the empty list because we will never start a contract again. We start all these 6 contracts in the beginning and then they just run and we interact with them. So no need to start new ones. Now we start providing the link between our model and the actual emulator, the actual contracts, the actual blockchain. And this is the first part of that is done by this instance contract function. So that first takes something type sym token to asset class. So this is the symbolic token stuff I mentioned that I don't really want to get into. And I'm also ignoring it here. Then we get a key, one of our construct instance keys, and a parameter value, which in our case is always unit. And then we must say which contract corresponds to this. So that's easy. So if the key is the start key, then it's the start endpoint contract. And if the key is the use key, then it's the use endpoint's double prime endpoint. And finally, this is now the last function we have to implement to provide an instance of this contract model class, is perform. So this tells how an action is actually expressed in actual action in the emulator or on the blockchain. So that gets the so-called handle fun, which allows us to get from contract instance keys to handles that allow us to interact with contracts called endpoints. Then again, the symtoken to asset class that we ignore, then the model state, the action, and then we must provide something in yet another monad called specification emulator trace. But you can think of that as just an emulator trace. It's very similar to an emulator trace. So maybe the start is the most complicated one. So let's maybe first look at the others. And all of these use this with wait helper function that I defined here. And the idea is just that that should ensure that something takes exactly 3 slots. So I can't simply wait for 3 slots. I mean, if I have an action that I want to perform in the emulator, if I knew how long it takes, how many slots, then obviously it's easy. I mean, if I know it takes 1 slot, then if I wait 2 more, then in total it's 3. But if I'm not sure how long this action will take, maybe it takes 1 slot, maybe 2, then I can't wait for an absolute amount of time. And this is what this with wait is for. So it's actually very simple. So it takes the model and the action I want to perform, and all it does is it performs the action, And the model, I showed you this before, has this current slot length. So I can check what the current slot was in the model, and I just add 3 and wait until that slot has been reached. So now, as long as this C action doesn't take more than 3 slots, this should always be fine. So if it takes 1, then here I will wait 2, and if it takes 2, then here I will wait 1, and so on. Okay, so using this, so all these things should then take 3 slots in total. And for example, for set price, I just call the endpoint set price, and this call endpoint function, if you recall from when we talked about emulator traces, needs a handle. And this is where this first argument to this function, this handle fun TS model, comes in. So I called that H here, and that just allows me to plug in one of my contract instance keys. So in this case, it's this use key VW. That's the contract instance I want to use. So the token cell run by V, and wallet W is the one interacting with it. So in putting that into this H function that is passed into this perform function, I get an actual handle. So now I can call endpoint set price on the correct instance of the contract. And the argument is P, the new price. And add tokens, buy tokens, withdraw are all exactly the same. So this really provides the links between my model and my actions with actual operations that are supposed to happen on the blockchain or in the emulator. Okay, and start is a little bit more tricky because of this mechanism I explained in the beginning, that when I start a token cell, I have to call this init endpoint. So this is what is happening here. First, I remember the handle for this start key V. Then I do what I did here in the other 4 cases as well. So I call the actual endpoint start for that handle. And the parameters, I can look that up. That's 2 more helper functions I have here, token currencies and token names, so that for a given wallet gives the currency symbol of the token that this wallet will sell, and the token name that this wallet will sell. Okay, so this starts the contract, the token sale. And now remember, the start contract actually writes the token sale into this observable state with tail. So now here I get to this observable state, and that's a maybe value. So if it's nothing, then something went wrong. The token sale didn't start, so I throw an error. But if it's just token sale, then now I can call the init endpoint for the use contracts that use this token sale. So I loop over all my wallets. I mean, it's only 2, but nevertheless. And for all the wallets, I call the init endpoint, look up the key for, I mean, the token sale and the wallet I'm now looking at, and call it with TS. And if you recall, so calling this init endpoint will actually kick off the original use contract, which was parameterized by TS. So basically the use contracts are waiting there, just exposing their init endpoints. And once I actually start the token sale, then I have this TS of type token sale, and then I can kick off the use contracts to be parameterized now by this token sale, and then interact with this token sale. And that's it. So this is the things you have to do, or at least in this case you have to do. Sometimes it's easier, it depends on the situation, to set up this contract model. And that's what is needed to do the quick check for Plutus contract. Now to tie everything together and use all the work we put into this, we can, for example, use this function prop run actions with options, which is in this Plutus contract test contract model module. And it takes check options, and we have seen those before. So those allow us to, for example, specify an initial fund distribution in our wallets, which we need because we have to provide the wallets with the tokens that are then later supposed to be sold. Then it also takes coverage options. So I showed you earlier this nice code coverage feature that has been recently added to this. So you can also use that for this quick check testing, but I haven't done that in this example. Then it takes an additional predicate to check at the end. So with the final model state, you can somehow provide a trace predicate, and then that will also be tested, but I'm not using that. And then it returns something of type action state to property. So I'm using this here, this prop run actions with options. I'm composing it with something coming from QuickCheck called with max success. So we can specify how many test cases to run. I think 100 is the default, so I wouldn't need that here, but this makes it easy to increase or decrease that. Right, as options, I start with the default check options, and then there is a lens going to emulator config, and another lens from emulator config to initial change state. And I set that to left D. So this is what we have done before. D is an initial distribution. And here I'm just saying every wallet should get 1,000 ADA and 1,000 tokens for all the tokens. So there are these tokens A and B. Wallet 1 is selling token A, wallet 2 is selling token B, but both wallets have 1,000 A's and 1,000 B's. And that's it. So now I have something of type actions to property. Property is also a quick check thing, but you can think of it as bool. It's like a beefed up bool that offers some like debugging and logging capabilities. But in principle, it behaves like a boolean. And we have seen before that we can randomly generate action sequences. So actions is just a type of action sequences. So we can randomly generate them. And therefore, this type is something that QuickCheck can handle. So if you apply QuickCheck to this prop TS, then QuickCheck will generate random action sequences and check whether the property is fulfilled. And the property that is actually checked is that what we say in this next state function, what happens to our model, that is actually reflected when we perform the actions on the blockchain in our emulator traces. So this will check that what we say should happen in the model actually does happen on the blockchain. Finally, I have this function here for use in the REPL test, which just applies QuickCheck to this property. So let's try this in the REPL. I execute test, and we see there was a problem. And if there's a problem, then we get a trace, and let's scroll up. And here we see the action sequence that caused this problem. So the action sequence after shrinking, see there were 11 tests and 8 shrinks. So the original counterexample that QuickCheck found was longer, more complicated, but then it was shrunk to get a minimal counterexample. So what is this counterexample? Wallet 2 starts a token sale. Then wallet 2 adds 8 tokens to the sale. And then wallet 2 tries to withdraw 3 tokens and 5 loveless. And that should fail. So nothing should be withdrawn because there are no lovelesses yet in the token sale. So accordingly, the expected funds change should be the wallet should use these 2 ADA, that's the minimal deposit, and it should lose the 8 tokens it put into the sale. But then QuickCheck informs us that what actually happened in the emulator trace was that we did indeed lose the 2 ADA, but we only lost 5 tokens. So that means that this withdrawal somehow didn't fail but succeeded. So we successfully withdrew 3 tokens of the 8. So now we're only 5 short. So there's a discrepancy. We did expect that the withdraw action would fail because there are no 5 loveless in there yet, but actually it succeeded and we did withdraw the 3 tokens, but no loveless. So there's something wrong. Of course, if something like that happens, there are several possibilities. It doesn't necessarily mean you have a bug in the code. It could also mean that you have a bug in the tests, that your model is simply wrong. But in this case, I think we do expect that what it says we expect, that it should fail and the 8 tokens should still be in the token cell. So let's look at the transition function again at the withdraw case. And all we are saying is that the constraint is must be signed by the correct wallet, and that afterwards we take out these N tokens and the loveless. But somehow there seems to be something wrong with it. And the reason has to do with this min ADA amount and the fact that state machines automatically adjust for that. So in our example, in this action sequence that QuickCheck found, there were the 2 ADA min deposit in there and then the 8 tokens. And now this constraint says afterwards there should be only 5 tokens in there and some ADA less, so less than 2 ADA, some loveless less that we try to withdraw. And now what the state machine will do, it will realize there is a UTXO that has less than the minimal ADA amount, and it will simply fix that and set it back to 2 ADA. And then the loveless we actually want to withdraw, we just don't. So nothing here will trigger an error. So we expected that this withdraw action would fail, but it actually doesn't. So the transaction will just be created that again has 2 ADA there and less tokens. So what I did is I fixed this. So I added another condition here. So not only do N and L have to be positive, I also check that V, that's the value in there, is greater than W plus the minimal amount of tokens. And what is W? W is what I want to withdraw. So I want to withdraw N tokens and L loveless. So I want that the value that's currently in the contract is greater or equal to the amount I want to withdraw plus the minimal amount of ADA. And in this example trace, the counter example that we found, this condition here would be violated. So this should not trigger, and we should run into the nothing case, so the transition is invalid and it should fail. And that means then that our model should be correct. So I updated the model accordingly. So instead of importing token sale, I now import the other model where I fixed this, that I called token sale fixed. So the names are all the same. So everything should still work. And if I reload and run tests again, then this time the 100 tests pass. We also get some statistics. So for example, we see which actions were actually tried. So we see that all of them were tried. We see how many of those were rejected due to preconditions. Then there's also a thing that QuickCheck automatically inserts weight actions. So there's the distribution of these weights, and it passed. Of course, that's not a proof that there's no bug in our code, but at least it gives us a lot of assurance. And if I wanted more assurance, I could increase this number 100 to a larger number like 500 or 1,000. Then, of course, it would take much longer. Finally, I want to show you how you can wrap all of this into a test suite. So this is now the main program of the test suite I'm configuring in my Cabal file. And it just, the main program just uses this default main from Tasty with tests, and test is now a test tree. where I use a test group, and I just put these two tests in that I have the emulator trace test that we saw beginning of the lecture, and now the quick check test. And I can run them with Cabal test. And we see everything passes.
Now, by default, this is all that the quick check tests do. So it only checks the flow of funds, whether that agrees at each point with what we specified in the model. But it is possible to add additional checks. And it is also possible to influence these action sequences. So right now they are just random actions, of course, checking the preconditions that we defined. But it's also possible to do some more unit test like scenarios where we specify certain flows of actions to steer the tests into certain directions. So that's called dynamic logic, and it's yet another monad, but I think that would go too far to talk about this now. And I should mention that, of course, this, even though it's very powerful, also has its limitations. So one thing is that, of course, it only tests the contracts that we provide. It doesn't test all possible off-chain code. So, of course, it's possible that with the provided off-chain code that we write, everything is fine, but some party could write their own off-chain code that allows them to steal funds from our contract. And obviously, this quick check model can't detect that because it has to use the contracts we give it in the perform method. And the second problem is concurrency.
We made sure that all the actions last exactly 3 slots, and they will happen neatly, sequentially, one after the other.
But of course, in the real blockchain or also in the emulator, wallets can have concurrent submissions of transactions. And in principle, we could try to do that with this model as well, but then we somehow must, in the model, specify what should happen in this case. And that might really depend on in which order the transactions are processed and so on. So that might get very complicated. So there are limitations, but nevertheless, it's a powerful way to test Plutus contracts.